Alright, so I want to talk about the integrated rate law now. The rate law, remember, shows the relationship between concentration and rate. What the integrated rate law is going to look at is the relationship between concentration and time. So if we want to know how much is left after a certain amount of time, we will use the integrated rate law and not the rate law. So the thing that stinks about the integrated rate law is that, well, it's actually kind of cool too, because it allows us to choose between them, but each order has a different equation. So for the first order reaction, this right here is the integrated rate law. The really nifty thing about all the integrated rate laws is that the equations follow a y equals mx plus b form. So what that means is we can graph it. Remember all of those graphs that I showed you earlier? It had, for each order, a different graph that would make a straight line depending on what values you're graphing. So for zero order, it was concentration versus time gives you a straight line. For first order, it's the natural log of the concentration versus time will give you a straight line. So you end up with this right here. And in this case, because the slope corresponds to k, if you know the slope of the line, you can find the rate constant. Now for zero order and first order, the slope is going to be negative. For second order, it's going to be positive. So if you want to find the rate constant, you have to remember to reverse the sign of the slope. But essentially, all this entails is you're going to get some data like this, and you put it into your calculator. Your calculator has the list slots, your graphing calculator, so there's like L1 and L2. And then if you just graphed those, that would be time versus concentration, which that would be a zero order. But if you want to find the first order, you have to take the natural log of the concentration. So in L3, you would do the natural log of L2, and then it would fill in the values. Now, I'm going to kind of skip over this because it takes a long time to explain, and I've actually made videos about this very thing. So if you're really confused, go ahead and watch those other videos where I walk through the step-by-step process of solving a problem like this. On this video, I'm just going to kind of talk about the equations, show them to you, and move on. It's not going to be very in-depth. The second order integrated rate law is this. So we have the inverse concentration versus time. So that would make a straight line like this over here when we graph the inverse concentration. So if you got data that had concentration and time, you would want to make sure you had a new column where you took the inverse of all the concentrations. And like I said earlier, second order is the only one with a positive slope, so it goes up. And so whatever the slope is, that is your rate constant. So once again, your equation would have data like this. You'd have to input it. So look at those other videos. Then zero order, like I've already said, is just concentration versus time. I saved zero order for last because we probably use it the least. But once again, k is the slope, but it's negative, so you have to reverse it. So what this allows us to do, if you make a graph, if you just make all three graphs or do a linear regression using each set of data, one is concentration versus time, one's natural log of concentration versus time, and one is inverse concentration versus time. If you do a linear regression of each of them, look at your correlation coefficient, which is the r-squared value. You want it to be as close to 1 as possible. So if you have a set of data and you put all of those into your calculator, do a linear regression of each scenario. Whichever one has a linear regression closest to 1 tells you that's the best line, and depending on which set of data you used, then you'll know the order. If this graph makes the best line, it's zero order. If this graph makes the best line, it's first. If this one, it's second. And not only that, but the linear regression will give you the slope, which in each case will allow you to find the rate constant. And if you know the rate constant and you know the order, you also know the rate law. So that's pretty nifty. Now, what's the point of the integrated rate law? I already mentioned this, but it's to be able to calculate how much is left after a certain amount of time, or how much time has passed given that we started with this and we ended with this. Or if we have this much time pass and we know our final concentration, how much did we start with? So you can take this a number of ways as far as what types of problems you'll be asked. All right, so for each integrated rate law, for each order, you're going to have a different half-life equation. Now, the easiest way to find a half-life, well, actually, it's probably not the easiest, but it's the one where you don't have to memorize the equation. You can simply put in a value. Oops, I don't like all that. I'm going to go to a different one. You put in a value for your initial concentration, then put in half that value for the concentration at time t, and then if you solve for t, that will give you the half-life, because it's the amount of time it took for half of that reactant to turn into product, for half of that reactant to go away, I guess, even though it's turning into something else. So you can do this with any of the orders. Whatever you put in for the concentration at time 0, right here, put in half that for time t, and then solve for t, and that is the half-life. Now, there are other equations that simplify this very thing for each one. And the most important one is the first order half-life. So this right here is the equation for solving half-life just for first order. This is actually the same as the integrated rate law. If you were to plug in 0.5 for the final concentration and 1 for the initial concentration, that would actually simplify to this equation right here. And that's true of all of these equations, but they simplify them specifically for half-life. So that's the first order. The second is the only one that, notice, it does not depend on any concentration. Second order does depend on concentration. Another way to write this would be 1 over k times the initial concentration. So what this means is that with a higher initial concentration, you have a shorter half-life. And as the reaction proceeds and you get less and less concentration, your half-life is actually going to get longer and longer. For 0 order, the rate never changes, right? It's a constant rate of reaction always. So what that means is, just to make sure there's no confusion here, like that, what this means is the more you start with, the longer it's going to take for half of it to go away. So that's why we have a 0 on top. The greater that number, the longer it'll take for half of it to go away. This right here is just for your benefit. It has all the equations we've talked about. And I think this is a good place to stop.